All right, guys. So today we wrap up Unit 4 in our Flipped Apes classroom. And we're going to be talking about Earth's geography and climate. And we're going to be talking about the phenomenon known as the El Nino or Southern Oscillation. So we're going to start out by talking about geography and climate and how geography shapes climate. So we're going to talk about we've already talked about how the sun's energy shapes weather and climate, but we're now going to jump into those geologic and geographic factors. We're going to talk about rain shadows, and we're going to talk about lake effect snow. So climate and geography. We've already said that most of our climate is determined by insolation, so that impact from how much of the sun's energy reaches the surface of the earth at that particular point. And we've said that the two main things that impact the amount of insolation are the angle of insolation, so how over what area the same amount of sun's energy is spread out, as well as how much of the atmosphere it has to pass through. So we know that that means that higher latitudes receive less solar insolation. They tend to be cooler, they tend to have less precipitation, whereas the equator receives the most intense insolation and it has higher temperatures, the air rises there, there's lots of precipitation. And of course, the latitudes with the lowest amount of precipitation are those that are 30 degrees north and 30 degrees south of the equator. But let's talk about how geology and geography also play a role in climate. So there's two main things that can impact climate in terms of geography. And those two things are mountains or mountain ranges and oceans or even large lakes like the Great Lakes. So our mountains are going to disrupt wind and they're going to produce something that we call the rain shadow effect. And oceans, as we know living here, moderate the temperature and add moisture to the air. If you have areas that are near an ocean, because water is such a powerful insulating factor, it can help to moderate their temperatures. Just as we see here in our area, when you're closer to the shore, you have smaller temperature changes over the course of the day, whereas farther inland, we have larger temperature changes over the course of the day because we don't have that insulating effect of the ocean. So let's first talk about rain shadows. So a rain shadow is produced when warm, moist air from the ocean hits the windward side of a mountain. When it hits that, obviously the air has to rise in order to go up and over the mountain. We know already that rising air cools, and so the water is going to condense and it's going to rain. So on the windward side of mountains, we tend to have very lush green vegetation. On the leeward side, or the away from the wind side of the mountain, the air tends to be very dry, and as it sinks down and there's additional pressure, it warms. And so on the leeward side of mountains, we have desert conditions. And a great example of this is if we think about California and Nevada. So California, at least some parts of California, get lots of rain. And as that air rises, because the prevailing wind direction is from the west, from the Pacific Ocean. And as it drops that moist air on the Sierra Nevada mountains, as it goes over, we reach the Valley of California, which is a desert, and we also reach Nevada, which is also desert. So if you've ever had the experience of going to Lake Tahoe or skiing at Lake Tahoe, when you're at the top of the mountain in the winter, if you look down to the westward side, which is the California side of the mountain, it's covered in snow, and where there's not snow, it's green. And if you look in the other direction, down the Nevada side of the mountain, there's no snow and it's a dry desert. And that's all an impact of the rain shadow. So we're going to look at a different example. This example is in South America. And we know that those eastern trade winds bring the moist air from the Atlantic across South America. So we're south of the 30th parallel. So we have easterlies, and it's bringing the rain from the Atlantic Ocean over the coast of South America. And as it runs into the Andes Mountains here, it has to drop all of that rain in order to rise up over the mountains and land on the other side. So this windward side of the Andes, now mind you, this has come all the way across the continent, but the windward side of the Andes is very rich and green with lots of heavy rainfall and lots of vegetation. Whereas the leeward side of the Andes actually has the Atacama Desert here because the air is very, very dry. And this is because of that rain shadow. Of course, we also have the 30th parallel running through the Atacama Desert, and we know that's where that cool, dry air is descending from the Hadley cell. So that also contributes to the fact that we have a desert here. And you can actually see this in satellite images. So this is the Atacama Desert, and you can see the Andes Mountains here. And so you can see that the rain shadow effect is very, very dramatic. And this is just an image of all of South America. And you can see that here at the 30th parallel, we are getting desert both on the westward side and on the eastern side, but we are also getting lots and lots of rain until you hit the Andes, and then you have the desert on the leeward side. And this is just an image. Even without being able to see the satellite, we know where the mountains are because we can see this dry area to the leeward side of the mountains. And we can see, reaching back to our conversations about tectonic plates, this is an area, a subduction zone. This is a tectonic plate boundary where the oceanic plate is being subducted under the continental plate, and that's what has pushed up and created the Andes Mountains, which then create that rain shadow. So these are our Andes here. Okay, so your practice FRQ, I want you to think about the regional precipitation pattern you'd expect for this portion of Mexico and Central America and justify your answer. Think about the prevailing winds. Think about what happens when warm, moist air, because this is going to very definitely be warm, moist air coming up from the equator. And think about how that is going to impact the land when it hits. Okay, and now we're going to move on to the last section in this unit, and that is 4.9, which is all about El Nino and La Nina, also known as the Southern Oscillation. So we're going to talk about what El Nino and La Nina are and how they are influenced by geological and geographic factors and how they affect different locations in different ways. Before we can jump into talking about El Nino and La Nina, we need to understand some of the basics of global surface ocean currents. So we learned about our global wind patterns, and the global wind patterns largely shape the surface currents of the ocean. So we see here, we have the equator in black, and we have the 30th parallel north and south marked in orange, so we can kind of see how all of those winds are related to these currents. So between 0 and 30 degrees, we have eastern trade winds that move the surface waters here from east to west and east to that move from east to west and east to west. And we can see that on the map, and they run into land masses and get diverted north. And then they're forced back. And so we get these large circular patterns that we call gyres. These are these circular patterns that are due to global wind patterns. And so in the northern hemisphere, the gyres always go clockwise. In the southern hemisphere, the gyres always go counterclockwise. And again, that's related to that wind pattern that's driven by the Coriolis effect. When we have areas where the winds blow the warm surface water away from a land mass. So here's an example here in the North Equatorial Current, as well as here in the North Equatorial Current. We have what we call upwelling zones, and that's areas that, because the warm surface water is being pushed away from the shore, something has to come up to replace it. So obviously the colder, deeper water is going to be pulled up to replace it. And if we think about what's in that deep water, that's where all of the nutrients from organisms that have died and fall into the bottom and decomposed, that's all in that deep water. So, and also the deep water is colder, which means that it has more dissolved oxygen in it. So these upwellings bring dissolved oxygen as well as lots of nutrients to the surface. Anytime we have those upwellings, then we have very rich fishing areas. And so off the coast of Mexico, as well as off the west coast of South America, the west coast of Southern Africa, and the west coast of Northern Africa, we have very, very rich fishing zones because of these upwellings. So the area we're going to be talking about with El Nino and La Nina is the Southern Pacific. So we're focusing on this area here south of the equator. Now remember, our currents are typically going counterclockwise south of the equator. And this is going to move that warm water away from the western coast of South America and cause this upwelling here. All right, before we jump into El Nino, let's talk a little bit about the global mixing that's caused by, that's caused by what we call the thermohaline circulation. So the thermohaline circulation is driven by two things. It's driven by differences in salinity across the ocean and by differences in temperature across the ocean. So our warm water moves from the equator, from the Gulf of Mexico towards the North Pole. And as it moves towards the pole, it cools and it evaporates. So that makes the water saltier and colder water is more dense. So it's going to sink and it's going to spread along the ocean floor. And it's eventually going to rise back up into shallow, warm ocean currents at those upwelling zones. And so we have this deep cold current and we have a shallow warm current. And living where we do, we benefit from this shallow warm current, and we call this the Gulf Stream. So we know that the east coast of the United States is warmed by the Gulf Stream, as is actually the western coast of Europe. Again, those upwellings bring all of that nutrients and oxygen to the surface. So if we were to look at the Gulf Stream warming the east coast of the United States versus the west coast of the United States, which has a much colder current, that's why it's pleasant to swim in Virginia Beach in the summer, and it's not very pleasant to swim off the coast of California. Even in the hottest months of the summer, their water is much colder than ours. And so if you look at Suffolk and San Francisco, we're at very similar latitudes, but San Francisco is significantly colder because of that thermohaline, because of the insulating effect of these warm water currents. By the same token, this warm water current crosses the ocean and it warms Europe. And so this is why, even though England is at a much higher latitude than, say, even Maine or Massachusetts, it is much warmer in the winter in Europe than it is in the northern part of North America. Okay, now with the basics of the oscillations down that ocean circulation, we can talk about the El Nino Southern Oscillation. So this is a regular pattern. It's a shifting atmospheric pressure pattern in the Pacific Ocean between South America and Australia or Southeast Asia. So this is a Southern Pacific phenomenon. So it shifts regularly from an El Nino to a La Nina condition. And an El Nino is a warm, rainy condition along the coast of South America. A La Nina brings cooler, drier conditions along the coast of South America. So usually there's a peak in El Nino and La Nina, and this can last for several years. So you'll see if we look at our most recent data here, that we had a peak of a couple of years of El Nino, and here we even had like 4 years of El Nino events. So this is not just a 1 year sort of a cycle, but a multi-year cycle. So let's talk about the normal conditions in so in a normal year, our trade winds drive the ocean circulation, so that we have cold water upwelling off the coast of South America, and that brings cool temperatures and good fisheries, which obviously has a significant economic impact. And that warm equatorial current brings heat as well as precipitation to Australia and Southeast Asia. So we're going to have high pressure in the East Pacific and low pressure in the West Pacific. In an El Nino year, the trade winds are going to weaken, and then they're actually going to reverse. And so that warm equatorial current that's normally driving water away from the coast of South America reverses and instead drives water back towards the coast of South America. And that's going to suppress that upwelling off the coast of South America, which obviously has a damaging impact on fisheries because there's fewer nutrients for the phytoplankton, which means that all the way up the food chain, we're going to have an impact, and that is eventually going to impact the fisheries as well. So it's going to create warmer, wetter conditions off the coast of South America and on the west coast of South America, and it's going to create cooler, drier conditions for Australia and Southeastern Asia. So we're going to have high pressure in the West Pacific and low pressure in the East Pacific. And then a La Nina goes all the way in the opposite direction, and our trade winds, our normal easterly trade winds, are stronger than usual, and it's going to cause even more upwelling off the coast of South America. It's going to be cooler than usual, extra good fisheries, and it's going to be rainier and warmer than normal in Australia and Southeast Asia. There are also impacts of El Nino and La Nina in North America as well. La Nina years tend to bring more Atlantic hurricanes. So there are impacts, but it's important to remember that El Nino and La Nina is a Southern Pacific phenomenon. So what are the effects of El Nino? It's going to suppress that upwelling, and it's going to result in less productive fisheries in South America. It generally creates a warmer winter in much of North America. It has a significant impact on the ski industry because those normal trade winds that bring that rain to the Sierra Nevadas and to the Rockies are dissipated. We do tend to have increased precipitation and flooding in the Americas, particularly South America, particularly the West Coast, but it brings drought in Southeast Asia and Australia. It brings decreased hurricane activity in the Atlantic and weakened monsoon activity in India and Southeast Asia. La Nina, on the other hand, brings stronger upwelling, better fisheries for South America than normal, worse tornado activity in the US, and more hurricane activity in the Atlantic, cooler, drier weather in the Americas, and rainier, warmer, increased monsoons in Southeast Asia. And your practice for this section is to describe 2 environmental problems related to the conditions of an El Nino event. And so that ends our conversation for today. If you have any questions, as always, let me know. I look forward to seeing you in class.